Hello, this is Greg Galson from Galactic Grays. I have a special guest today, Les Johnson. Les Johnson is a longtime friend of mine from decades. He is a spectacular space scientist and a renowned author of both fiction and fact works. And he is a principal investigator on the NEA Scout, which is a Near Earth Asteroid solar light sail that's going to sail on the pressure of sunlight and go to an asteroid and be launched as a secondary payload from the Artemis-I mission. And this payload, my friends, it's going to be awesome because it fits in something the size of really like an oversized shoebox or a boot box maybe. And it's going to unfurl a major large mylar foil that is going to be pushed by sunlight to an asteroid. So not only going to the moon, we're going to an asteroid. My friends, I'm going to give you Les Johnson. Les, tell us about NEA Scout.
Well, thanks, Greg. Appreciate you having me on. And it is good to see you. I was thinking the other day, we've known each other almost as long as I've been in Huntsville, which has been quite a while. So it has been. Yeah, we don't need to keep saying the word decades, okay? You gave a great introduction. NEA Scout is the next in a line of solar sail. Actually, it's the first real mission of a solar sail. We've had some demonstrations before, but this will be the first time that anyone's tried to use a solar sail as a primary propulsion system to get from point A to point B. Just for listeners that may not be aware of what a solar sail is, you gave a pretty good introduction. The light that's all around us, sunlight, the light from the camera, the light that's falling on me right now is consisting of photons, little particles of light. And those particles, while they don't have rest mass, they do have momentum. And if you think of these little particles like little BBs and bouncing off something, when they do that, they lose a little bit of energy, and that energy is pushing whatever they reflect from. So just like if you go sailing out on Lake Guntersville or any lake or the ocean, and you have a sail, the wind hits the sail and bounces off of it, the sail recoils, and that's what pulls the ship, right? The ship's attached to that via the mast, and so the wind pulls it, and you're pulled along or pushed along by the wind. Well, we're not using the solar wind, we're using sunlight. And as the light reflects from a big lightweight reflector, it looks like an aluminum foil, and it's not. I can explain what it is here in a minute. The light will reflect from it and it'll push it. And you can use that to accelerate a spacecraft in space. Now, don't be confused though. The light, or not confused, just to be clear, it's a very small push. The light outside, the light in your room, even though it's pushing on you, you can't feel it, and it's really hard to measure because it's so much smaller than all the other forces acting on us. Gravity, the wind currents in the room from an air conditioner, or if you're listening to this in the wintertime, the furnace, all of those forces are stronger than the force of sunlight. If you go out on a sunny day, clear blue sky, and you look at all of the pressure of all the light falling on 2 soccer fields of area, it's the same pressure that you would feel on your hand if you put a quarter on your hand. So it's really not much. But when you get out into space and you're away from all these other forces, you've got plenty of sunlight, and you're given enough time, that constant push can accelerate a spacecraft to some pretty high speeds. And the Near Earth Asteroid Scout will be the first time that we've not just deployed a sail. That's been done several times. 2010, we did it here at NASA Marshall with the NanoSail D in Earth orbit. The Japanese flew one called Icarus. They deployed in deep space. Want to give credit to the Planetary Society, that private space organization headed up by Bill Nye. They did 2 deployment demonstrations in Earth orbit. But NEA Scout's a 2-year operational mission. We deploy our sail after we get off of Artemis-I. We have to fly to an asteroid, and we have a camera on board provided by my colleague at JPL, Dr. Julie Castillo-Roget, which is going to do science at an asteroid. So we don't just deploy the sail, we have to actually steer, navigate, and control the sail for about 2 years so that we can study an asteroid and learn more about the neighborhood.
Wow, that's exciting, Les. Well, I'll be excited to see this video you've got, and also would be exciting to get updates along the way. Maybe you can come back and tell us it deployed, it's doing well, and finally when it gets there and you start getting some science about it out of it, we really want to hear all that too. So you said you had a video you just want to show us?
I do, and I can narrate it for you. Let me see if I can get it to play correctly here. Hold on just 1 second. I have to switch to the right screen, so bear with me. I just made you too small. What did I do with the video? I know I copied it over. Here it is. And I'll pull it up on the other screen. You get your pause it. All right, let's see. Share screen. Where do I do that, Greg?
There's a big green button, should be at the bottom.
Oh yeah, I see that.
Dead center.
All right, share. Do you see the rocket?
I see the rocket. Looks good.
All right, let me get you started here.
Except it don't.
Right.
It's got a white tank, so.
There we go. So if you can still see it, this is an artist. Of course, this is an animation because the rocket hasn't flown yet. We're still waiting. But on the SLS, the Space Launch System for the Artemis-I mission, of course, the primary mission is to send the Orion capsule to the moon and demonstrate the capabilities of this big rocket, the biggest rocket since the Saturn V. So as it goes to space, you know, is typical, what's going to happen is it'll lose the solid rocket motors. And then after the initial burn is complete, the stage that's going to give the translunar injection and take the Orion capsule onto the moon does its burn to head on getting the Orion, you know, toward its destination, which is to loop around the moon a few times to demonstrate that capability and show that we can bring the Orion safely back to the Earth with crew. And there'll be a future flight that they fly on. But that upper stage, after the Orion is on its way, nestled in the top, you can see here are what are 10 little launchers, each which contains what looks like a box. It looks like a big boot box. And that each of these is a small spacecraft. There are 10 of them. And they are about the size of a boot box. The NEA Scout is one of those 10. And after it's ejected from the SLS, it'll just basically float free in space till it's stabilized. We'll keep it from tumbling. And then it'll go around the moon. After it's out there, the solar panels, not the sail yet, will deploy and generate power to recharge the battery. And there's also an antenna on one of those panels that'll pop open so that it can communicate with the Earth, and we can test all the comm system. There go the panels. And the top of those panels contains the antenna array. And it'll call home. And that zoop you just saw is the deployment of the 925 square foot sail. I'm going to pause it because we had that happen pretty quickly for the video, but it's actually going to take the better part of an hour for this sail to deploy. Let me rewind it a little bit so you can see that again. There we go. And this is to scale, so you can see how much larger than the spacecraft the sail is. Now, this sail is packaged in the middle. It takes up 1/3 of the spacecraft. And this material looks like aluminum foil, but it's not. And it's not mylar. It's a plastic that's radiation resistant called CP1. And it's covered with aluminum, so it looks like aluminum foil. But if you were to hold it, it would really feel like a saran wrap that's not sticky. It's pretty thin, pretty lightweight. So that's all folded and then put on a roll in the middle of the spacecraft. And then we have 4 booms that are metallic. They're like big tape measures that are coiled up on a deployer, and they slowly are pushed out, one in each corner. And as they're pushed out, the sail is attached to that, and it slowly takes the sail from the spool and unfurls it. So it'll take about 40-45 minutes all told. We'll probably stop a few times during the deployment to get the sail fully unfurled. And once it's out, we'll test our ability to tip and tilt the sail using something called reaction wheels on the spacecraft. And we also have a way to move the sail relative to the spacecraft in kind of an XY direction. We call it the active mass translator. And that lets us kind of change the amount of light falling on this side of the sail versus this side. And if this gets a little bit more push, it'll tilt the sail more this way. So we're going to be dynamically adjusting that during flight. And I think we show a bit about the AMT moving here in just a minute. Now you'll see we have the sail, looks like it's in a slow spin. That's really not that accurate. It won't really be spinning. We would lose control over it if it were. It's just a perspective thing that the artist put in there. The sail will deploy. We're actually going to be hanging around the moon for a while in a highly elliptical orbit until the asteroid that we want to go to is in the right position. And then we'll slowly increase our distance from the moon and fly out toward the asteroid. The cruise to the asteroid after the sail is deployed will take about 2 years, okay? And this asteroid we're going to is one called 2020 GE. And that'll be the smallest asteroid that we've ever visited, anybody has. Oh, there you go. You can see the sail tipping and tilting. That's how we steer. A sail goes in the direction that the light pressure pushes it. So if you want to go in a different direction, you have to subtly adjust the angle with which the light reflects from the sail in order to steer. And we show kind of an exaggerated movement of the sail as we're flying along there. And then after 2 years, we'll reach the asteroid. And we have a camera provided by NASA JPL, which is going to image the asteroid to learn more about what it is. Is it one big rock? Is it a bunch of small rocks that are loosely gravitationally bound? Does it have pebbles on it? What exactly is it made of? Just basically learning more about the neighborhood. So that is the NEA Scout mission in a nutshell. Let me see if I can, I'll leave that up there and just let you look at it and see if you have any questions or if there's anything I left out, and then I'll.
Yeah, well, that's beautiful. Now tell me, how thick is that sail?
Well, for those people watching, you can see I'm follically challenged. It's about the thickness of a human hair. Okay. And the material, if you're handling it, if this were an in-person lecture, I'd hand around a piece of the material. You can touch it, hold it, fold it, roll it, and you probably won't damage it. You might put extra wrinkles in it, which, by the way, from a thrust performance point of view, is not a good thing. So we want it to be as flat as it can be. But the sample I hand around, you can feel of it. Now, if you try to damage it, you can. You could poke your finger through it. You could rip it. It was pretty funny. I had it at a talk, and I just handed it out, and I told people, you know, by handling it, you won't break it. And before I got to the part about you can break it if you try, some woman poked her finger through it. And I think I looked aghast because everyone laughed at my reaction. And then she felt really bad. And the material went on around the room. But, you know, so if this material, if you try to damage it, you can, but just handling it, it's pretty robust.
She took it as a challenge. She didn't think it hurt it, I guess. So it's the thickness of a hair. And what, I take it it's aluminum. What kind of aluminum is it?
Well, it's got an aluminum coating on it. It's just aluminum. It's a plastic coated with about 100 angstroms of aluminum.
Now you said the plastic is ZP1. It's radiation hard.
It's called CP1.
CP1.
Right. It's and it's a real exciting name. Clear polyimide 1. Real exciting name. You know, you would think they would name it something like, you know, Zarathustra or something, right? But it's clear polyimide 1. It's a proprietary material by the people who manufacture the sail, which is a company called Nozzle, and they're located here in Huntsville. And they're the folks who built the sunshade for the James Webb Space Telescope. And our sail was assembled in the same facility that they used to build the sunshade for the JWST.
So if they come out with a third iteration, it'll be C3PO, right?
Yeah, well, maybe. They are Star Wars fans, so I wouldn't be surprised.
Well, that is interesting. That's actually a lot thicker than what the solar cell people would love to make. I know you'd love to have something like an atom thick, but that would be kind of hard to come up with unless you got graphene. You can one day make large sheet graphenes, but even then you're going to be probably 2 atoms because you're probably going to spray aluminum on that. I don't know how tight graphene would be against light. I know some people have talked about maybe when you have some kind of vacuum deposition process that would vaporize the plastic on the other end or heating it afterwards. What's the ultimate thinness you think you could get a light cell down to?
Well, you said it, 1 or 2 atoms thick. Just so your audience can understand why that's so important. Solar sails have a very small push. If I were to take a spacecraft of the same size as a NEA Scout, let me back it up, in this little box, and you were to take out the third of it that the sail is packed in, and you were to replace it with the most efficient rocket that we make, maybe an electric propulsion system or a really good chemical thruster, and you were to put it side by side with the NEA Scout and say, you know, we're going to have a 2-year race here, and you say, go. The one with the rocket is going to go and be gone. right? And in about 3 seconds, it's going to run out of fuel and you're going to be moving out of sight. You won't see it, right? And you're going to look at us and you're going to think, is this thing even going to move, right? And you come back a few days later and you see that it has moved and it's moving a little faster each day, but it's still basically just barely moving. But give us about a month, we will pass up that rocket propelled spacecraft because they ran out of fuel and they have nothing else to accelerate with, and we're going to pass them and wave as we go by. So it's really the tortoise and the hare. And if this is a sprint, we're going to lose. If it's a marathon, we get a lot of propellant. This propulsion, this sail, for those that speak rocket scientist language, gives us a delta V of about 2 kilometers a second. And a chemical system that's on that other spacecraft hypothetically might give you a few single meters per second of delta V, and we're going to give kilometers per second.
For the uninitiated, delta V is what you raise your orbit with, or decrease it if you have a negative delta V. It's if you go higher and farther, you need more and more delta V. That's how the orbital dynamics work.
And a lot of people, it's really just it's an acceleration. It's a change in velocity that you can give with a propulsion system over time. And so it's like, measuring the acceleration of your car. But not exactly, because you might use delta V just for moving up and down, not necessarily doing a lot of velocity change. But what's really challenging, Greg, is the force of sunlight is small and it's constant at any given distance. So the only equation I plan to throw out at people here is one that most people have probably heard. Force equals mass times acceleration, F equal ma. Right. And for a given area of sail, this 1,000 square foot NEA Scout sail, there's only so much sunlight that falls on it, so it only gets so much force. So if you want to have a big acceleration, the spacecraft has to have a low mass, right? F equal ma. The force is constant, so to get a big A, you got to have a low M. Right. Well, the sail is not very heavy, but it's a lot thicker than a single atom. But if you want to get the ultimate thrust out of the sail, you want to have a really lightweight sail. And when I started working on sails in the year 2000 or thereabouts, the idea of building a sail a square kilometer, which is what I'd really love to do, in the year 2000, where we looked at available materials that had the tensile strength and the durability to be able to do that, the only thing we could find was something called unobtainium. So it was all science fictional. There was no material out there that met the requirements. That all changed in 2004 with the isolation and characterization of graphene, which you mentioned earlier, which led to a Nobel Prize in 2010. But that changed the game. Graphene is a material that's just carbon, but it's a single atom layer thick. And it's the strongest material that we've ever really encountered. It's 300 times stronger than steel by weight. And to just give you an example, if you have my NEA Scout sail made from a single atom layer thick sheet of graphene, you could put an elephant on it and it wouldn't break the sail. Okay. Wow. That's how powerful, that's how strong.
Or a little lady with a sharp fingernail either, right?
Well, yeah, you could poke a hole. Probably not, actually, with the graphene. It'd be really hard to do that. So ultimately, what we want to do is build an extremely large sail to capture as much sunlight as you can, made out of something like graphene, maybe with a single atom layer thick aluminum or a couple atoms thick aluminum to get good reflectivity on the surface. Right. And deploy that as close deploy it as close to the sun as you can to get as much sunlight intensity, because the sunlight intensity goes up as you get closer to the sun. And it doesn't just, if I cut the distance to the sun in half, this physics lesson for the day, the total amount of light falling on that sail isn't doubled, it's a factor of 4.
4 times more. 4
times more. So if I go 1/4 the Earth's sun distance, I get 16 times as much pressure. So what you want to do is you want to go really close to the sun where it's really hot. And the good thing is graphene will survive, right? So the challenge for future sails, which is not something we can build today, but I think is physically possible, we just have to figure out how to engineer it. And my engineering buddies hate me for saying that. But theory says you can do it, is make a sail made out of graphene, but we don't know how to do that yet. And if you can, then you can get extremely high exit velocities, and you can actually think about sending a solar sail to Alpha Centauri with a trip time of hundreds of years rather than tens of thousands of years, which is what it would take with a chemical rocket. But that's all in the future.
So tell me, the graphene, it does have, it's like a Buckminster fullerene rolled out in a flat sheet. So there is holes in it, or I imagine that the holes are going to let the light pass through where it hits a hole, and where it don't, it would reflect.
Now,
So
be careful. It's not Buckminster fullerenes. Those have been around for a while.
yeah, I understand, but what I'm saying is kind of the idea if you folded one out flat. I mean, there's a pattern. It's got like there's a grid pattern to the whole thing. How they
There is.
there's holes in the middle of it. So right. So how big are
yeah, and that the ability of light to pass through that's going to depend on the wavelength of light relative to the side of the gap. And I'm not really sure what that is. That's a good question. That's why I'm thinking you
get the same thing with the antenna. Radio waves will reflect on the antenna with a large grid pattern if the wave is large enough. So it's just
that's right. But the thing about this is that you probably won't use just graphene, because graphene itself is semi-transparent, and what you want is reflective. So we're going to have to coat it with something to make it reflective. And so you're probably going to have a few atoms layer thick aluminum or something else sprayed on the side of it that would keep that effect from happening, if it's even possible. It just depends on the wavelength of light.
There's people that's played around with graphene and Buckminster fullerenes and other structures and adding other elements into them to make different compounds. So maybe we'll have a whole new compound similar to graphene in the future that might be more reflective. So, the material science in this area is brand new. Any young person wanting a bright career, this is one area to go into. So I think it's really exciting what can be done. Now, what's the largest sheet of graphene that we can make right now? What's our state of the art?
Well, that's just it. A pure graphene, probably a few millimeters.
It's not very big. We haven't mastered large-scale sheets of graphene.
No, not yet. Now there are companies that are making graphene oxides and are doing some of these compounds you're talking about where they dope it with different things, and they're making larger sheets of graphene. But it's not pure graphene, and therefore it doesn't have all the. It's still great, but it's not as strong as pure graphene would be, or have the electrical conductivity that you would have with pure graphene. So there are different ways people are messing around with this. Yeah.
All right. Do you see us getting there with pure graphene? Do you think we'll be able to master that one day and figure out how to make?
Absolutely. There's no physical reason we can't. It's a matter of engineering, really, and that's a matter of investment and trial and error. And the Thomas Edison thing. Thomas Edison knew it was physically possible to build a light bulb. He just didn't know what the right combination of materials and vacuum was to make it work. And he and his team eventually found that right combination. But from a physics point of view, they knew a long time before they built it, hey, this will work. They just didn't know exactly how to make it work, right?
So if you want to be a millionaire and you can crack this code, you got it made, right?
No, I don't know. There's a lot of investment in graphene. I don't know if you know this. I wrote a whole book on graphene, and it is astounding, the investment. And the number one investors right now are the people who make your cell phone.
Oh yeah, they're looking at battery, super capacitor, which you use in lieu of batteries too.
The battery, not only that, but can you imagine a screen? It's a conductive material, so they could make an atom layer thick screen that would never break.
Wow.
Okay.
You can fold it probably make a foldable phone. So these rigid things we got.
And it'd be really lightweight. So yeah, there's a lot of research on the order of billions a year going in by private companies into graphene research and development, trying to find products and how to bring things to market with graphene.
Well, there's a lot of career opportunities there. That's exciting. Wow, I want to build these big balloon facilities floating in the Venetian atmosphere, and there's so much carbon there. If you're the big balloons, you can lay out a huge platform underneath them, and you can manufacture giant sheets of graphene if we figure it out.
Hey, I'm in.
The solar system, that'd be our main product. Would be large scale graphene sheets. Get them up into orbit around Venus and just launch them out to Jupiter. Any other user. So, yeah, this is a very exciting list. The cool thing is that some people, K. Eric Drexler was writing in the 70s on ideas of taking light cells out to the asteroids and using that to bring them back in. The idea of tacking, just like you would with a sailboat against the wind, to bring something back down into the inner solar system so we could bring asteroid materials close to Earth. I guess on the downside is you got to worry some of these asteroids being the rubble piles, you'd be worried that there would be bits and pieces flying around that might hit your solar cell your light cells, I like to call it, usually it's because people think solar cells are thinking photovoltaics. So the language here is a little persnickety. But what do you think about the prospect of mining asteroids, bringing them back with a light cell?
Well, Greg, before I answer that question, I have to remind everybody that I'm speaking here today as a private citizen, not representing NASA's point of view, right?
Bingo, bingo. Yes.
Yeah, I may be working on it when I'm talking about NEA Scout. Yeah, I can be talking about NASA, but it occurs to me I'm sitting here in my man cave, right? And I've got, stuff sitting around, and you're asking me about prospecting asteroids, and NASA's not really doing that right now. So I've got to give the caveat that this is just less thinking about the future. Yeah, that's right. And you can do that. And in fact, when we conceived of the NEA Scout mission, it was back during the proposal was actually written for this back in the Obama administration, when we were thinking about sending people to visit asteroids. And the notion was we wanted to have a way to do low-cost reconnaissance of many asteroids to find suitable targets for people to go to. And then as we started doing that, there were these startup companies that popped up that were looking at mining asteroids. Luxembourg has gotten really involved in this notion of asteroid mining and what they want to go do, providing resources to commercial space stations, maybe to the lunar moon village. And so the whole notion of having an affordable, low-cost way to go do surveys is viable. And these little CubeSats, these small spacecraft that weigh about 20 pounds, some of which might be propelled by a sail, some by solar electric propulsion, to go survey a lot of asteroids to find good candidates for mining is really a low-cost, affordable way to do that.
That's exciting. That's exciting. So, one of the biggest things that governs whether an asteroid can be economically mined or not is the fuel to get to it and bring it back. This might make it a tractable thing. There are other people such as Dr. John Lewis at I guess he's in Arizona State University, if I remember right. He's been writing for decades about, various other means to be able to lower the fuel cost of bringing one back, such as aerobraking and things like that. And he thinks he's found, pathways that make it plausible. Of course, the near Earth asteroids are a lot easier to get to, much smaller delta V than the main belt asteroids. But there is that one, like, what do they call it, Psychic, that's thought to be rich in platinum group metals and gold. That's got a lot of people excited. It's thought to be a planetary core, essentially, of a larger planetoid that got busted up.
And there's a mission going to Psyche. I think the mission is called Psyche, right? Or something like that.
Right, there is.
He's going here soon, yep.
And I mentioned that in a previous video here on this channel. So that's going to be an exciting mission, just to see what that thing's made out of. But the whole idea of mining anything in the main belt means you've got to be able to get to it at low fuel cost, and to be able to get there and back with something like a light cell would be a tremendous thing. Now, I think it takes a long time to tack in to the solar system, according to some projections I saw a long time ago. It could take maybe several years to tack back in. But essentially, all you got to do is you're removing delta V, so you're thrusting against your orbit, essentially. So I don't know why it really should take so long. The gravity should pull you in when you thrust against your orbit.
Well, actually, Greg, one of the cool things about solar sails that's kind of counterintuitive is that they are better at thrusting toward the sun than away from the sun. And that's because
gravity works for you then. So
gravity works for you, and that inverse square law of light works for you. We talked about the sunlight gets stronger as you go closer to the sun, and it gets stronger non-linearly, right? So
square law.
Yep. If you deploy a sail here at the Earth, and you decide you're going to go to accelerate to move away, you have to remember everything in space is moving. And when we launch a spacecraft from the Earth, which is going, if my head's the sun, everything's orbiting the sun, and we deploy anything from the Earth, it's got all the orbital velocity of the Earth already with it that it's got as it goes out into space. So when you deploy that sail, if you tilt the sail to give you extra thrust in the direction you're already going, you start spiraling away from the sun. But as you move away, the light pressure starts dropping off pretty rapidly, all right? So if you tilt it the other way, so that you're decelerating, you're thrusting opposite the direction to which you're moving, you start falling toward the sun, and the sunlight pressure gets faster and better as you get closer. So you start falling faster and faster. So a solar sail is probably better to go to Mercury than it is to go to Mars, which is kind of counterintuitive. Most people think if you put a sail out here, it's just going to go away from the sun. But once you consider the orbital dynamics and everything moving and the sun's gravity, it's actually easier to go toward the sun than away from the sun.
Mercury should be a cool object to go to, because if you want metal to make your cells out of, there should be a lot of that there too.
Absolutely. And there are a lot of interesting things revealed by Messenger about Mercury's dark side, right? Far side, and a lot of cool stuff.
Well, Mercury is, I guess, is it totally phase locked into the sun, just like our moon is?
I believe it's tied
ratio,
just like the moon is. Yep. So there's a side that's always facing away from the sun.
I wasn't sure if it had like a ratio 2-to-1 or 3-to-1, or if it was.
Well, I'm not a planetologist. A planetary.
There is craters though that are permanently in the darkness in the north and south poles, and ice has been detected on Mercury. Mercury, the closest planet to the sun, is cooler than Venus.
At parts of it, that's right. Yeah,
parts of it. It's got ice. It's got ice on it. So
and no greenhouse effect.
Well, it's got water ice, no greenhouse effect, and it's got water ice. So it might actually be a place that people could settle on the surface. You can settle Venus, you just can't go on the surface yet. So take some major terraforming to maybe some good sunshades to be able to get down to Venus on the surface. But yeah, it's pretty exciting. Les, I'm really excited about this because this has got a lot of potential for the future, and you're on the very cutting edge of it. I'm just happy to know somebody that's doing this your whole life. You've been one of the few people that's been on those forward-looking science projects, the far-end propulsion. You've always been interested in the deep space, interstellar travel, and you've led a lot of research in that area through your positions at NASA. You've had some very interesting career there. And I'm just always excited to hear what you've got to say, because you're always a fresh wellspring of information. And you're making
flattering me, Greg. Keep flattering. It works, right?
But you make it happen. You not just talk. You're out here making things happen, and I really appreciate that. So we've got a bright future if we can just not do something stupid on this planet for now. If we can just keep our heads level enough that we don't blow ourselves up, we can have an awesome future down the road. And I'm looking forward to that. And guys like Les are the beacons for what the possibilities are and for actually making it happen. So Les, I really thank you for coming on this channel. I really admire what you do, and I'm proud to call you a longtime friend. And just keep it up, and let's hear back from you from time to time. And if you got other things you'd like to talk about, no, this isn't your only cup of tea. You've got a lot of things going on, Les. So yeah, we'd love to hear from you from time to time. Come back and tell us what you got cooking, what's exciting you, because anything's exciting you is probably going to excite my audience here.
Well, I appreciate that, Greg. I'll tell you, I feel really blessed. I've had a wonderful career at NASA. NASA's enabled me to work on some cutting edge technologies, been involved in some flight experiments, working with some great people. It doesn't, it's not without its frustrations. I mean, it is U.S. government, which is the biggest bureaucracy in the world, maybe the second biggest next to China. I don't know. But, and you have to worm your way through that. But once you kind of accept that you have to deal with that, there's still a lot of opportunity to do really interesting things that I really sincerely hope are moving the needle forward for our capabilities in space, for not only science and exploration, but development and eventually settlement and expansion. I mean, that's what's always motivated me.
Well, that's what I've always been about, is space settlement. That's always been my top interest, is how do we get out there and start living there. So this gets us a step closer and be able to get the resources we'll need and make it more affordable to get around.
Let's hope. So thanks a lot for having me. I look forward to talking to you again.
Les, thank you again. Thank you very much. Everyone, please subscribe to my channel if you're not already done so. And I do have Les in an interview he did for HAL 5 in a previous video. Y'all can look for that. And thank y'all for watching, everyone. And with that, I'm going to say Greg, goodbye, and Greg out.
All right. Bye-bye.
Bye-bye.